Hello everyone, my name is Cho Yiqi. Today I want to introduce this paper. The title is A Plausible Model for the Galactic Extending Ray Emission, Graphene Exposed to Far UV Light. This paper was published at the Astrophysical Journal in 2023. This is my outline, including introduction, materials and instrument, result and discussion. And this paper proposed a plausible model for extending rate emission. And finally is conclusions. Let's introduce extending rate emission first, also called ERE. ERE could be observed in a wide range of interstellar environments. He first observed a red rectangle in 1975, like this picture. It emits range from 500 to 10,000 nanometers. It exists in far UV dominant astral environment. There are three kinds of ERE models. First is classical photoluminescence, and it usually uses visible laser and its photoconversion efficiency is less than 100%. But in realistic, ERE exists in far UV, so it is not reasonable. And second one is recurrent fluorescence. It requires large molecules with low laying state, so still it has limits. Finally is two-step process, but it cannot explain redshift of ERE bands in far UV radiation. So the ERE models is uncertain. And let's introduce graphene. Graphene is two-dimensional materials composed of single-layer hexagonal carbon atoms. It exists a strong sigma and pi bond with sp2 hybridization structure. And optical properties of single-layer graphene could be altered by structural defects. For example, photoluminescence intensity. In this paper, choose single-layer graphene to study. And this slide will introduce what is synchrotron radiation. Synchrotron radiation is generated when a charged particle traveling at the nearly speed of light, for example, electrons. In National Synchrotron Radiation Research Center, first we'll inject electron in booster ring and through the transmission line to storage ring. And the electron gone in booster ring linking to the beam line to do experiment. This paper used third generation synchrotron radiation, which is applied insertion device. This is Yablonsky diagram. It explains simply principle of fluorescence. A ground state molecule absorbs the photons to excited state. After internal conversion or relaxation, it will emit the fluorescence. It has a lot of characteristics. First, it follows spin selection rule, and it needs to fix the excitation wavelengths. Important thing is a non-destructive optical technique. The process is less than 10 nanoseconds. It will measure the light emission after relaxation. Its advantage is it can understand the sample band gap and detect the defect. This is a table compare the PL and PLE spectrum. PL will fix its excitation wavelength and to detect the emission range, and PLE is fix the emission wavelength to scan its excitation range. Both of it can provide some information such as emission properties and absorption-emission relationship. It can application in bandgap and defects of sample. The most important thing is that PLE is complementary to PL spectra. Let's introduce the sample. The graphene sample were purchased from SES material. The graphene will use chemical vapor deposition on copper and after wet transfer onto NGF2. It can get a single layer graphene on NGF2. The reason why this paper chose NGF2 to do experiment is because that previous study didn't investigate the single layer graphene on magnesium fluoride. The other reason is that it is stable and is not easy to moisture. This figure A1 is PL spectra of magnesium fluoride at various wavelengths and 10 Kelvin. Only when wavelength excitation in 200 nanometer exists photoluminescence. In-house instruments including Raman and AFN. Raman is home-built micro. Raman consists of a microscope, monochromator, CCD detector, laser at 532 nanometer. AFN is setting to taping mode with this resolution. And other light source is TLS-03 from TLS-03 of the National Synchrotron Radiation Research Center range from 100 to 350 nanometer, and TLS-21 is for far UV light treatment. This is schematic diagram of TLS-03. PL and PLE experimental were performed at TLS-03. Synchrotron radiation from here to this chamber, and heat sample and detect by PNT. Different beam size lead to different photoflux, and far UV treatment use TLS-21. There is high dust and medium dust photon flux treatment. It will discuss after result and discussion. This figure shows the PL and PLE spectra of SLG on magnesium fluoride. Focus on the A part without far UV treatment. It can observe that PLE of graphene is transparent to photons when wavelengths bigger than 170 nanometer and 10 Kelvin. This is complementary with PL. In PL, the excitation wavelength bigger than 130. There is no emission. So this PL process is excitation from sigma to sigma star and luminescence from pi star to pi. The results of APAR are consistent with previous study in here. After 170 nanometer, there is no transparent to graphene on magnesium fluoride at 10 Kelvin, the red line. Let's focus on B part. Single layer graphene on magnesium fluoride with far UV treatment 4 hours. The energy source is 118 nanometer. After 4-hour treatment, the sample emerged a black spot like this. And PLE generate a new asymmetry band might be pi-to-pi star transition. PL spectra of far UV treatment is similar to the A part, but the intensity increase might due to the structure defects. In Part C use high-dose exposure to investigate the PL enhancement of single-layer graphene. So PLE probe at 750 nanometer. The absorption range from 120 and 314 nanometer. This might because graphene quantum dot could emit wide range of light, so PLE of C part is wide range, and the PL of C part is redshift to 750 nanometer. Its FWHN is about 78 nanometer. This is complementary to PLE spectra, and this might relate to electronic state and internal conversion of electron. In previous study, Raman spectra have been used to examine the quality of graphene. In previous study, G band is in plane vibration mode, and D band is graphene defect. 2D band is second-order overtone in plane vibration. So in A part, the pristine graphene without D band, it shows that the pristine graphene is defectless and exists G and 2D band. And in medium flux treatment 4 hours, the D band formation confirmed that single-layer graphene with defects after far UV treatment. And the ratio of these is about 60.2. That indicates that graphene defects origin from far UV exposure. And C part is high flux photon treatment. After high dose treatment, Raman band becomes broadening, and the weak 2D band might generate from graphene quantum dot. In previous study, investigate. The morphology can be detected by AFM. The A part is before far UV treatment. The B part is with medium dose far UV treatment 4 hours. C part is high dose far UV treatment 4 hours. So before far UV exposure, single-layer graphene is uniform and flat. And after far UV treatment, there are numerous grains with particle size 20 to 16 nanometer. Its height about 5 nanometer. After exposure, the single-layer graphene becomes grainy and randomly distributed holes. So let's compare the light source. So to confirm the effect of far UV treatment, this paper still uses different light sources to irradiation single-layer graphene. First light source is LED, and the second one is D2 lamp. After irradiate single-layer graphene, the result shows that PL and the Raman spectra show there are defects of single-layer graphene. Although the total photon dosage are twice of far UV. So far UV light is the key role for graphene as prospective EIE carrier. By combining previous study, this paper proposed a plausible two-step model for EIE. So let's consider first step condition. Only far UV light source can break the CC bond and create carriers defect. EIE carriers might be PHA or larger size similar to graphene molecules. And high-dose far UV may generate graphene quantum dot structure. Let's consider two-step model, the second part. Six-step condition. The graphene defect emit photon in the EIE range when this range, far UV and EIE band. In 10 Kelvin condition, the quantum yield is bigger than 30%. In this picture, PL spectra of far UV expose single-length graphene and magnesium fluoride substrate in different temperatures. Red light is 10 Kelvin and black light is room temperature. The red light is bigger than room temperature. And in this paper, PLE spectra range from far UV to visible, like C part. So the PCE issue is solved, better than classical model. Classical model is photon PCE is less than 100%. And still have other factors to be considered, such as photon flux. PL spectra of single-layer graphene medium flux are more broadening, and medium flux lead to various size graphene flake nanoparticle forming. And this high flux treatment is similar to nebula like this NGC and this NGC. Both of these are nebula, so graphene might be the carrier of EIE. Here is my conclusions. Graphene or large PAH are carriers in this model. Only far UV could break graphene, causing defects. Photon flux also impact the results. In this paper conclusion, they are further investigate target is formation and doped or all-doped graphene. Thanks for your listening.